integrals over rectangular regions. Okay, so we introduced the idea of the double integration. And this was perhaps the thing which most naturally follows on from the one variable integration that we did last year. So a double integral like this, the double integral of a function of two variables over some region R. R is a region in the xy plane, which is the domain of the function. What this object corresponds to, this is what we talked about this morning, is this cylindrical type subvolume of R3 lying in R3 over the region R in the xy plane and bounded at the other side by the surface defined by the function, by the surface z equals f of xy. Now, the first example of these we looked at was the particularly straightforward example where the region of integration was a rectangle which was aligned with the coordinate axes. Meaning it's a rectangle and two of the sides are parallel to the x-axis, the other two parallel to the y-axis. So such a rectangle is defined by these four values: the left and right limits on the x-axis and the forward and back limits, if you like, on the y-axis. And for such simple regions, the way we evaluate these double integrals is they naturally turn into this pair of nested integrals. Okay, a pair of nested integrals where you've got one integral inside another one. Now, we spent some time this morning explaining how you link this pair of nested integrals to this diagram here of the surface and the cylindrical volume lying underneath the surface. Okay, this inner integral, where we integrate with respect to x from a to b of the function f of xy, this integral corresponded to the cross-sectional area where you take a slice through that cylindrical volume parallel to the x-axis, positioned at a certain y value. So you slice it down parallel to the x-axis with the knife located at a certain value y along the y-axis. And this inner integral then is the integral, is the area of that vertical cross-section through the cylindrical volume. And as such then, when you integrate that area from C up to D with respect to y, what you're doing is you're summing up all of those cross-sectional areas through this three-dimensional volume from the front face of it, located at y equals c, all the way through to the back face, located at y equals d. And summing up those cross-sectional areas gives you the volume of the region. Okay. So it's important when you're doing this to understand and to think about the link between the kind of algebra you're doing on the page with the integrals and geometrically what they are representing in the graphical interpretation of the function, which for functions of two variables is this surface defined by the function. Now, of course, we might ask, what happens when the region of integration is not so straightforward? What happens when we're looking at non-rectangular regions? Okay, that's what we're going to look at now. But first of all, any questions or queries about the rectangular case that we just looked at? Okay, so we'll go on now to describe some of the things that can happen when we look at non-rectangular regions. Well, we're still going to integrate the double integral, this volume over a region in the base plane underneath the surface. We're still going to evaluate that as a pair of nested integrals. But when the region of integration is no longer a rectangle, the limits of integration can get more complicated. Okay, instead of just being four constants, that a, b, c, d in the previous example, because the region is not a rectangle, it can be more complicated. So let's take an example. Let's look at integrating this function here, f of xy, which is 4x cubed plus 4y cubed, over the region R in the xy plane, and we're given some boundary information for it. We're given 3 boundary curves for the region. X equals 2, y equals 1, so those are straight lines parallel to the x and y axes, and the curve y equals x squared. So when you plot those 3 curves in the xy plane, which is what's shown over here, we got the curve x equals 2, which is that vertical straight line. We've got the curve y equals 1, which is this horizontal line. And we got the curve y equals x squared. So you can see I've marked out in heavy black line there the region R, which is bounded by those 3 curves. So it's this triangle-like region, okay? Looks like a triangle, except it's not exactly. It's got 2 straight sides here, but of course this side, this hypotenuse, in quotes, side, isn't a straight line. It's a curve described by y equals x squared. So it kind of looks like a triangle, but it's not. Okay, so let's just call it, we might refer to it as a triangular region. So you can think, now we've got the xy plane drawn on the page there. You can imagine the z-axis extending out from the origin straight towards you. So this function f defines a surface which is lying here above the xy plane. Okay? So integrating this function, f of xy, over this region will be calculating the volume in this cylindrical region. Okay? Now we still turn it into a pair of nested integrals, and this is what's shown here. So we're taking the double integral over R of f of xy dx dy. So that means the inner integral is with respect to x, and the outer integral is with respect to y. Now what we have to explain here is the presence of these 4 limits of integration. Now, it's very much the case that when you're figuring out these limits of integration, you work from the outer integral in. So the first thing to think about is, why do we have the limits y equals 1 to 4 here? Well, we look at the region of integration, and we ask ourselves, between what values of y do we have to integrate in order to capture the region R? Okay? And it's clear from the sketch that you need to consider all values of y between 1 and 4. Okay, that's where the region is located, inside this horizontal band across the xy plane between y equals 1 and y equals 4. So the limits of integration for the y value are from 1 to 4. But then you look at the inner integral. Now remember, what is this inner integral? This inner integral is giving us the area of a cross-section through the cylindrical region above the plane located at a particular y value. So we think of a general y value between 1 and 4. I've marked a cut here that you might slice the thing through here by this light gray line. Okay, so here's a cross section through this region located at a particular y value. Then we ask ourselves, well, if we want to capture the area lying over this line, between this line and its projection on the surface, we need to integrate from this x value here all the way up to this x value here. So you ask yourself what those are. Well, what's the x value here? Well, if this strip is located at the position y, this x value here is the square root of y, okay? Because it comes from the point lying on the curve y equals x squared. So the relationship between x and y is that x is the square root of y. The upper limit for the x integration is x equals 2. Okay, so you're going up as far as the limit x equals 2. And that description of the limits of integration for the x variable, that holds, that's valid. That description from square root of y up to the value 2, that's valid for all the values of y in the relevant range, i.e. between 1 and 4. So once we've decided on that, then we have our pair of nested integrals, so we can go ahead and integrate it. Now the inner integral is with respect to x. You're treating y as a constant, so the inner integral becomes x to the power 4 plus 4xy cubed. Then you need to evaluate that at the given limits, at the square root of y and 2. But those are limits for the x variable. Okay? So we substitute the value x equals 2 into the integral function, and the value square root of y into the integral function for x, and then we subtract those values. Now we're substituting constants and y values for the x variables, so what we're going to end up with is a function of y. Okay. So after making the substitutions and gathering like terms, well, there aren't really any like terms together, we end up with this polynomial in y here. Okay, and that's the inner integral completed. And the inner integral is a function of y. Gives you the area of the cross-sectional slice through the cylindrical region, but at varying locations on the y-axis. So it's not surprising that this area has a dependence on y. And then it's more straightforward from that point on. We're just integrating this cross-sectional area from y equals 1 up to 4, summing up all the areas of those cross-sections to get the actual volume of the cylindrical region. Okay? So you perform this integration in the normal way for an integral of a single variable function to bring you to the total integral, 745 minus. Now, this integral can also be taken in the opposite order. This is example 1.20. So integral can also be performed in the other order, meaning not having x as the inner integral and y as the outer one, but the other way around. Okay, so there the integral, okay, we're still integrating f of xy, but now we're going to have y as the inner integral and x as the outer integral. This was y equals 1, x equals 2, and then it was y equals x squared. This is this one here. So this is the point 1 on the x-axis, and this was the point y equals 4. So this was our region R here. But now, what we just have to be careful about is figuring out what the appropriate limits for this presentation of the double integral is. Okay. Now this is one integral inside the other one. The inner integral is the y integral, and the outer integral is the x. We work from the outside in. Between what limits of the x variable do we need to integrate in order to cover the region R? Well, it's clear from the picture that there are portions of the region R located everywhere between x equals 1 and x equals 2. Okay, that vertical band between x equals 1 and x equals 2 is where this region R is located. So this integral should be carried out from 1 up to 2. But now what the inner integral is going to be, the inner integral is going to give you this cross-sectional area through the cylindrical region from a cut through a slice through the cylinder, but this time going parallel to the y-axis. And it's located at a particular x value. So you imagine a given x value here, some value of x here, and the region is cut at that x value. And what that means is we've got a particular range of y values that we need to integrate over in order to cover the region at this particular x value. Now you have to focus in on a particular x and at the same time think about all possible x's as well. Now where do these vertical strips start? Well, it's the same case no matter what value of x you take. These vertical strips always start at the y value, y equals 1. So we have to start integrating at y equals 1 in the inner integral, and we have to integrate up a certain amount. But the amount we integrate changes. For low values of x, we don't integrate up very far at all, because if we go any further, we'll be outside the region. But for large values of x, x near 2, we have to integrate a long way. We have to go nearly all the way up to 4. Okay, so there's a dependence on x for the upper limit of this inner integral. What exactly is it? Well, the y value that I want to pick out is this y value over here. And what is that y value? Well, it's the y value of this point on this boundary curve. But this boundary curve is the curve specified by y equals x squared. Okay. So this value on the y-axis is the square of x. If x is the location of this line, this vertical slice through the region located at the x value x, then the y value has to be x squared. So we integrate, the upper limit for integration is the x squared as well. So you see that changing the order of integration for non-rectangular regions is not so straightforward as it was for the aligned rectangles. For the aligned rectangles, which we saw this morning, to change the order of integration, you simply take the integration signs and the differentials and flip them. Okay? Nothing else is needed. But for non-rectangular regions, okay, you are taking the integrals and the differentials and flipping them, but you need new limits of integration. Okay? You don't simply flip the limits of integration as well. You have to invert the functional relationships coming from the boundary curves. So the original order, we were integrating y from 1 to 4 and x from square root of y to 2. But when we do it in this other order with x on the outside, you're integrating x from 1 to 2 and y on the inner integral from 1 up to x squared. Okay. And as an exercise, if you carry this double integration through, you will get the same value as you got in the original order. Is that okay? Any questions on that at all? Is there anything on that you'd like me to clarify for you? Okay, we're going to stick with this theme for the moment. I won't go on and do any other new topics. But I'd like to look at some more examples of this. So these examples aren't in the notes. These are just extra ones. The first example I'd like to look at is to integrate the function f of xy. Now just take the product of the two variables. So x times y. Integrate this over the triangle with vertices. I'm going to take the point 0, 3, 0.11, and the 0.53. Okay, so those three vertices, those 3 points in the plane will define a triangle. And I want to integrate this function f of xy, which is x times y, over that triangle. So the first thing to do here that we should do is to produce a nice sketch. Okay, so it's to sketch the region of integration. So when I say over the triangle, I mean, or the region in the plane that I'm integrating over is the triangle spanned by those three vertices. Okay? So we sketch the region of integration. So we need a nice xy plane to fit these points into. Now we got 3 points. We got 0 up to y equals 3, 1, 2, 3, and x has to go up to 5. So we got 0, 3, 1, 1, and 5, 3. Approximately here. Okay, so here's our region of integration, R. 1, 1, 5, 3, 0, 3. Now, there's 3 boundary curves there, 3 boundary lines, and it may indeed be useful to know what they are. Well, the top one is easy. The top one is just a vertical line at y equals 3. It's the equation of that curve. And this line here at the bottom right, well, if we take the ratio of changes in coordinates, we'll get the slope of it. This is y equals, it's going to be y equals mx plus c. The slope of it is the y difference is 2 divided by the x difference, which is 4. So 2 divided by 4, so it's got slope of half. So it's a half x, and what's the constant? Well, if x is 1, it has, so the constant is a half as well. That's the equation of that line. And we also want, or we probably will want, the equation of the other line. So this is y equals mx plus c as well. This, of course, has negative slopes. It's sloping downwards. And so it's a ratio of the y change over the x change is the gradient. So the y change is minus 2, and the x change is 1. So it's got slope minus 2. So this is y equals minus 2x. And when x is 0, you've got 3, so it's plus 3. Okay, so that's the equation of that boundary curve. Okay, so we've got a nice sketch of our region, and we completely know everything about it. It's a triangle across these 3 vertices, and we've obtained the equations, the kind of formula descriptions of the 3 boundary curves. So we want the integral now. We want the integral I, where I is the double integral over R of xy dx dy. And we're free. We should think a little bit about how we're going to order the integrals, whether we're going to have x be the inner integral and y be the outer one, or the other way around. So I'll use we have to think about dividing this region R into horizontal strips or vertical strips. Now, if you think about decomposing the region into horizontal strips, here's a few of them, these green lines. You can see nice behavior there in that these horizontal green lines across the region, they always start on this boundary curve and end on this one. And that's different behavior to what happens if you think of the region split into vertical strips. Because when you take vertical slices through this region, vertical meaning with respect to the y-axis, then something different is the case. Sometimes, for the first part of the x range, the vertical strips start on this boundary curve and they end on the top one. But then once you get past x equals 1, the behavior changes. Then the vertical strips are starting on this boundary curve. They're still ending on this one up here. So there's a kind of 2 different types of behavior there if we make x the outer integral. So the splitting the region R into horizontal strips looks slightly easier there, slightly more approachable. So I'll choose to make x the inner integral and y the outer integral. I'll show you what happens when you split it up the other way as well. This way looks perhaps the simplest at the start. So you work from the outside in, you look at your diagram and you say, well, between what values of the y variable, because that's the outer one, what values of y do you have to integrate between to capture R? Well, we've got to start at this y value and we've got to go all the way up to that, okay? Because that's where the region is located, in that horizontal band between y equals 1 and y equals 3. We've got to integrate from 1 up to 3. Then you got to think about these horizontal bands. These are the horizontal slices parallel to the x-axis located at various y values. Okay. So the inner integral, if you like, accepts the value of y from the outer integral, because that's where it is. It's inside the scope of the outer integral. So the outer integral gives some particular constant y value to the inner integral. And then these limits of integration have got to be determined by that y value. So we have to start integrating with respect to x on this curve and end on this one. So for low y values, we're only integrating over a little bit of x. But as y increases, we're increasing the range of x we're integrating over until when y gets to 3, we're doing the full x integral from x equals 0 all the way up to x equals 5 to capture the very top slice of the region R. Okay. So these limits of integration, I'm expecting functions of y that go in. And all they are the functions of y that corresponding to those lines. Now, present there, I've got them described as y as a function of x, so I just got to invert them and describe them instead as x is a function of y. So what's this is equivalent to x is equal to, so this is y minus a half multiplied by 2, so 2y minus 1. And this one here is equivalent to y minus 3 divided by minus 2. So it's minus 1/2 of y plus 3 over 2, all right? Okay, so those are the same lines, but just described the other way around, x in terms of y. And so those are our limits of integration. I want to start integrating on the x-axis from minus 1/2 y plus 3 over 2. That's the lower limit of integration. And the upper limit of integration is 2y minus 1. Okay. So I start the x integral at minus 1/2 y plus 3 over 2. That will start it at the correct point here, corresponding to the beginning of the triangular region at that level of y. And I'll go up as far as this value, 2y minus 1, which will go up as far as the correct point on the x-axis to just bring me to the edge of the triangle at that certain y value. Okay. So all these green horizontal strips, they're all located at a particular y value. Okay. Is everybody clear how I came to that description? Any queries about it at all? Things, aspects of it you'd like me to clarify? Okay. So I was free to make the inner integral either the y integral or the x integral. I just had to choose. This choice looks slightly more straightforward because it's always the same description for the start of the green horizontal slices as it is, and always the same description for the end of the green horizontal slices. So now we're ready to charge ahead with the integration. Integrating x times y with respect to x gives us the integral x squared over 2. So we've got x squared over 2 times y. And we're substituting in these lower limits, 1/2 y plus 3 over 2. And the upper limit is x equals 2y minus 1. It's sometimes useful to not just write the value of the limit, but actually indicate which variable it is to be substituted for. That can be a good thing because a common slip up that people might make when they're operating these, when they're evaluating these, is they take this upper limit and they substitute it in for the wrong variable here. So we've just done an x integral. These are the limits of integration for the x variable. When we're doing the substitution into the integrated to the indefinite integral part, you need to substitute these expressions in for the correct variable. So these are going in for the variable x. We're just keeping that y there. So still leaving the outer integral y alone. We haven't started that yet. So you've got 2y minus 1 all of it squared times y over 2 minus 1/2 y plus 3 over 2 all of it squared times y over 2. And then you're integrating all of that with respect to y. Okay, that looks a bit messy and all over the place, but it is, after all, just, well, the brackets give you quadratics in y, and you multiply them again by y. So you've just got a cubic polynomial in y there. Cubic polynomial in y. Yeah, I thought I worked it out already, but I haven't. Okay, 20 to 6 on a Monday evening is not a good time to see me try and expand a cubic polynomial. So, I mean, I'll just leave it there. But from that point on, the integration is clear. Okay, multiply out the brackets, you'll get a cubic polynomial in y. Integrate that, it'll integrate to a power and order 4 polynomial, and then evaluate it at the limits 1 and 2. Okay. What I want to show you, what I don't want to rush through, I want to take the time I've left, is show you how we express the integral with respect to the other order. So evaluate this in the normal way from now. Alternatively, we could have expressed I as the following. So I is the double integral. So I'm integrating x times y, and now I'm going to make y the inner integral and x the outer integral. Now, I alluded to this already. When we look at the region of integration, this time, when you express the double integral as this pair of nested integrals, okay, first we look at the x variable, because that's on the outside, and you look at the region and you see, well, we have to integrate all the way from x equals 0 all the way up to x equals 5. You have to go between those limits of x in order to capture the region R. Okay? So we can imagine putting, although I won't put it yet, as you'll see shortly why, we can imagine putting 0 to 5 here. What the hell, let's just put it there, 0 to 5. Because it's correct, x is going to integrate from 0 to 5. So then we have to think of these red vertical strips. These are the cross sections parallel to the y-axis. This inner integral here is going to give us the area lying over this region R underneath the surface at each of these vertical slices. But we run into a bit of a problem here. These vertical slices, they always end at 3. But the question is what I put down here. Well, you don't put a question mark, but there's a question about what goes down here. It's not clear, because sometimes the red vertical strips start on this line, and they do that for a while at the beginning. But then the behavior changes, and then the red strips are always beginning on this, on that third side of the triangle. Okay? So there's no single expression that you can put here that can capture that. Okay? Some of the time you want minus 2x plus 3, and the rest of the time you want a half x plus a half. So you just can't do it in a single expression. So you need to break it apart. So we can't realize it as a single pair of nested integrals. Everyone familiar with the way I'm using the word nested? It means like one inside the other, like those Russian dolls. You have one doll inside another one. This inner integral is inside the outer one, so they're nested. So you got to split it up. You got to separately think about the x variable between 0 and 1. In other words, integrating it over this left-hand smaller triangle. Okay. And then separately, go from 1, continue on from 1 up to 5, integrating xy, dy, dx. Okay, so we now need 2 pairs of nested integrals. And now there's no problem with filling in the y limits. So when x is between 0 and 1, the red vertical strips are beginning at the value minus 2x plus 3. Remember, that's a value for the y coordinate. It's a value for the y coordinate located at a particular x coordinate. So at this value of x, the red vertical strip has to begin at this point over here, which is minus 2x plus 3. And the vertical strips always end at y equals 3. Always ends at y equals 3. But these vertical strips, everywhere for x between 1 and 5, they begin at a half x plus a half. Okay, so you see that behavior there. If we had, when we do choose to realize the double integrals as a pair of repeated integrals, sometimes these are called repeated integrals or nested integrals, we're forced to have 2 of them. One to capture the left-hand bit, one to capture the right-hand bit, okay? Because there's different behavior in the 2 bits, being different at the lower limit for the y variable. Okay? And we would then integrate these as before. Okay. Now integrate this inner integral with respect to y, so you get xy squared over 2. And after substitution, it becomes a polynomial in x, which you integrate from 0 to 1. And in the second repeated integral, the inner integral again integrates to xy squared over 2. So you're integrating with respect to y. You perform these substitutions for the y variable. It then becomes a polynomial in x, which you integrate from 1 to 5. So an exercise for you is to complete this and confirm the same value for I is obtained in both orders. And then if you look at, in terms of tutorial exercises, you look at exercises 1.6 and 1.7, there's, well, we haven't covered all of the stuff for 1.7 yet, actually. Actually, in 1.7, you're ready to do questions 1 and 2 now. You can do questions 1 and 2 on exercises 1.7 and all of exercises 1.6. Okay, so there's plenty to be working with there in advance of your next tutorial, be it Friday or next Monday. And we'll do some more, well, we need to do more work with these double integrals in our lecture next week. So far, we've just been using the Cartesian coordinate system, x and y. That works fine for rectangles and triangles, but as soon as anything circular starts coming into the picture, we'll need to be able to switch to the polar coordinates. So that's what we'll talk about next time.